Good morning, all.
Morning.
Good morning.
How's everybody?
Doing well.
Good. Good. Let me clean up a little bit and we'll get started. It's definitely a Monday for me. All righty, let's see. Megan, you are up first today. So you are now co-host. All right, take it away.
Let me make sure I pull it up. Okay. Oh, my computer's not wanting to work with me very well. Okay. Okay. So I want to talk to you guys about shipping container homes in the general way that they are built. So I did a presentation step by step of like a way to build your shipping container home. Typically there's two types of shipping containers you can get. There's one trip only and as is. As is containers can be dangerous. They can have chemicals, they can have rust. So generally speaking, you don't want the as is containers. The best ones to get are the one trip only, and most are built one trip only. A huge step in all this would be designing your plans and deciding if you want to stick to one shipping container. If you need more space, it's always a good idea to do two, just because they're very small and it can be hard to incorporate a lot of space into a very small container. So like I said, choosing to do two, how you want to connect the two, if you want to put them side by side or kind of differentiate them a little bit, can be a good idea based on several things, like if you want one room to be bigger or one room to be smaller, or just kind of want a general big space to hang out in or spend time in. What type of foundation you might want to use depends more on the ground area around you. Most people for shipping containers use the pier because it's just cost effective and they're kind of quick and easy to set up. Slab is obviously better if you live somewhere the ground isn't as stable, and strip is just kind of a step in the middle if you need a little more stability than the pier. If you want to connect your shipping container homes, like connect two or more, you can do this by welding, or you can use, like I saw a lot of them with that they built a middle space with just like kind of like a house in the middle, but just connecting them and making more space, and that can be good also for plumbing if you wanted to run more than one plumbing line. Most of them only have one, and then it runs it throughout the house. And then you need to cut your holes in your shipping container because obviously this is a big box. There's not much in it, so you need holes for like your door or your windows. And there is typically one plumbing line, like I said, that goes into the house, and then it's run either underneath stuff or through the framing, just to prevent extra heat loss due to going through the metal container. That's a huge escape for heat loss in these things. Obviously, another big thing is you want to strip out the flooring. Most people don't want the flooring in the original shipping container home because it's got damage done to it, either through water damage or it might have contained chemicals. You just don't really want to keep the same flooring in these houses. So the framing, you need to be careful when doing the framing in these homes, because if you screw into the metal, that can help you lose heat, and you really don't want to do that, especially if you're in this house is going to be located in a colder area. So you kind of want to screw into the flooring or into just other parts of the framing just to keep that heat from escaping later down the road. It can be really complicated to install insulation in a shipping container home because these walls are so thin and they don't really have a lot of room to put insulation in. Typically speaking, most people would want to do spray in insulation in these, but if you wanted to be more sustainable, you could use cotton or wool, or I've even seen some that did cork with it. So it's really up to you depending on what you want to do, but spray in is the best known one to do. After you install your insulation, you can go ahead and add your windows and add your doors back. You just go ahead and set it up, and you can paint it, but a big factor in all this is making sure your shipping container won't rust. So preventing rust, you could do things like use just a paint that does not allow for rust, or using a special spray that prevents rust. And it is recommended that down the road at some point you do paint again with the rust-free paint, just so you're still trying to prevent it, and you don't, eventually they're going to rust if you don't take all precautionary measures to prevent that. Obviously you need to put up framing for bedrooms and things of that sort. Adding the plumbing, like I said, you can go through the framing. Typically these have one line, but if you do add the middle section, you can run lines up through that middle section floor. But the plumbing typically goes through the walls just to prevent heat loss from going up through the bottom of them. Obviously, you'll want electricity in your house, so you'll call out your electrician and get him to set up either a temporary line, or you can choose to set up with green power. That's kind of up to you. I did try to do a cost estimate for this. I gave my uncle, who's a contractor, a call, and I asked him what the initial price for just to set up with Duke Energy would be, and he says it's usually just the cost to come out and set up, drop a temporary line. And he didn't really give me a general price because he says he generally just factors that in with everything else. And then that's your price per kilowatt hour, which is $10. And then Your solar panel, obviously you don't pay anything if they are installed on your house, but the initial cost can be between $30,000 and $60,000. So it can be a lot initially. So setting up solar panels might not be for everyone, but it is a possibility if you want to be more green, and typically people who build shipping containers, that's something that they would want to look into. Something you need to keep in mind when building a shipping container house is, after the framing, installation, and sheetrock, you're looking at a building that was pretty thin to begin with, and now it's going to be even thinner, just because of all that space that everything took up, and especially, insulation can add a lot or it cannot add a lot depending on what you choose. So your shipping container, while you may buy it thinking, oh, this is plenty of space, it actually might be a lot smaller than you think. Oh, I feel like I'm missing a slide. But well, why might you want to build this? There's a lot of creative freedom to the design to the house, because obviously you get to pick everything that goes into this house, and the general shape of them creates a lot of room to build however you want. They're cheaper houses. The cost to build is around $10,000 to $35,000, which is a whole lot cheaper than your typical house. If you ever needed to move them, you can put them on a trailer, especially if they're smaller, and move them quite a bit simpler than regular houses. Some of the pros is they have a low price point compared to typical houses, and they can be faster to build. These take, depending on how much time you're looking at building, regular houses can take years, well, a year, depending on how great your contractor is, but these are pretty quick. Obviously, they're designed for buyers, so anything the buyer wants, they can have like room set up, or a setup in certain ways, or just have them really small, or have a really big room, or just have like a general just big space where it's all open. And they can be placed on trailers and be kind of like a tiny house-ish kind of thing, but that's less common for sure. They don't require as much land as traditional housing, because obviously they're smaller, and they hold their value typically over time. They're, like I said, it can be really hard to install insulation on these. So a very common complaint you hear is that it's too cold, and my insulation doesn't work as well. So that might be something you want to consider if you live in a really cold area. You might not want this type of house because of the lack of insulation can be really detrimental. They are typically smaller, so if you have like a 8-person household or more, you might not want this type of house. Not that it couldn't be built for you, it would be kind of a bigger mess to create, and it might just not work for your needs. So a lot of the shipping containers have chemicals in them that are not great for the environment. And these containers, just making them into shipping containers can be good, but sometimes they just, in general, are just continuing to buy shipping containers might not be the best idea. So they are environmentally friendly in the sense you recycle them, but they aren't if you get ones that are very chemically, like have a ton of chemicals transported in them. They can rust, and no one likes the look of a rusty house. So trying to get rid of that rust would be a big burden on some people. And they can tend to have structural issues just where the corners weigh down over time. And these are some different designs for shipping container homes. Oh, and this is an extra step. This moved, but you can design storage. You might want to design storage into them. Obviously, everyone knows about the staircase, where you can put in just little areas underneath your stairs to add in extra storage. And then there's my citations.
Keep forgetting to unmute myself. Very good. So a couple of questions. Let me see if I can find that one where you mentioned it. Well, I don't see it right offhand, but you said something about middle space. What do you mean by middle space?
Okay, so in a lot of, I looked up a lot of videos of people like building these at home, like with their significant other or whatever, and they would build a little like wooden, like obviously like a regular house in the middle to connect the two halves of the shipping container homes. So they would have like a regular house in the center, and then it would connect the two shipping containers on the sides.
I got you. Okay, kind of like common ground, common room.
Yeah, like common ground.
Okay. Yeah. So what about, okay, so I see a lot of pictures where, we're seeing the, the exterior siding on it. So did you come across any that done a lot of exterior siding? I noticed this one had wood on the outside of it. But are there more choices for external stuff, or did you see most of them being, just the container exterior?
So I saw a lot more of just the container being the exterior, but I'm sure there are tons that you can do siding with. I would have to do more research on it and let you know.
Okay, cool. Just so you know, I don't know, you probably are not aware of it, but your audio is horrible. I mean, it's just, and it's a technical issue, I'm sure. So, sometimes you kind of really kind of squabble out, but I think for the most part, we were able to hear you. Did you find any issues with condensation?
I didn't find any specific information on that, no.
Okay. And the reason that I want to talk about that for just a second, I'm finding, dealing with this school bus, I'm finding that it's a whole different ball game than what I'm accustomed to. And my computer is running a little slow as well for some reason. I'm not rightly sure. So as soon as it comes up, so we haven't really got to moisture in talking about that, but in a regular conventional house, we have a couple of things. We've got siding, we have our sheathing normally, and sometimes we have a thermal barrier there if we've done our good, build. We've got our stud cavity, and then generally we got interior finish, which could be gypboard and so forth. So what's going on in here is, we breathe, and when we're breathing out, we're breathing out moisture, and that can build up. We're boiling water, we're taking showers and all of this. Now let's, we're comfortably 70 degrees in here, and it's 38 degrees here outside currently. And so what happens is this air, is going out through here, and vapor is detrimental. And at some point through here, we have an imaginary line. At some point, this warm air that has moisture in it is going to drop dramatically down. And let me give you an example of that. So this is a psychometric chart, and this is how we determine at what point does water condensate. Now we know that in the summertime we go outside with our sassafras tea, and we're sitting out on the veranda, and it's a nice warm day. It's got a lot of moisture in the air, and our glass is just dripping wet with condensation. So let me explain to you what's happening here. So like I said, the inside air is 70 degrees, and that's where this is. I'm reading a dry bulb down here. So most of the time when we talk about the temperature, we're talking about dry bulb, not wet bulb. And then the outside temperature I said here is about 38 degrees. So that's about right in there. Okay. So let's say, for instance, all right, so my relative humidity right now is 51%. And that's what these curved lines are. So there's 50%, and right there's 51. Okay, now remember, it's 38 degrees outside. So and pretend like this is, pretend like this is the wall, okay? This is inside, this is outside. And as this air, let me change colors here. As this air goes through the wall, when it gets to this point right here, that is your saturation line. In other words, all the moisture that you had on the inside of the wall here from taking a shower, baths, boiling water, breathing, so forth, is transferring through that wall. And when it reaches this temperature, which it just so happens to be 50 degrees, all of this moisture or all this vapor in the air here will condense. And it will condense on whatever that we have. If it's, if we're talking about the sheathing or the studs, it's going to condense to the studs. If it so happens to be right in through here, then our insulation is going to get wet. So that is always and forever going to happen, and that's why we talk about vapor barriers. Now let's look at this. Let's look at this metal thing going on here. So we got this piece of metal out here. And inside we may have, a stud layer, and we had we were talking about blown in insulation, and that's fine, or not blown in, but sprayed insulation, spray foam. All right, so we got our spray foam in there, and then we might have whatever finish we got in here, gypboard. In a bus, can't exactly do gypboard. And you were talking about moving these containers after they were built. If you're planning on building it, don't use gypboard because it's going to crack. So now, instead of all of this woody stuff, okay, so wood has an R value of 1.25 per inch. And metal has almost zero. It's 0.03 if I remember correctly. So you were talking about, you know, really painting the crap out of this stuff, and that is super, 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 super important, because now we've got this 70-degree weather, and you know it's 50. Where's that 50-degree line? It's almost always on that piece of metal, because metal is a conductor of energy, of heat. So it's gonna, you know, it's gonna suck the living crap out of the heat in here. And when this moisture hits that right there, that's where it's gonna cling. And so, you know, even in this bus, what you said, you know, strip out the floor, absolutely. Instead of just, you know, don't stop at just the floor, you need to strip out everything on this, you know, to make sure that you get right down to the metal, find out what kind of rust you got going on there, and paint, and more paint on all this metal to protect it from rust, because that is going to be the biggest issue right there. Something you also said was when you are attaching your framing, when you're attaching your framing, you don't think about it much, but when you're doing that framing, and again, you got that really thin piece of metal, and you're trying to put some studs in here, and you go to screw those studs into the metal. So in this case, I'm gonna put my screw on the outside and screw into it this way here. So you don't think about it much, but these are bridges. So what's gonna happen is we got this nice, you know, warm heat in here, and this heat is going to get sucked out the end of those things. Now you think, well, we're talking about the end of the screw, which is literally probably about that big. All right. So, but the thing about it is, I love talking about this and using this analogy. Let me find, I want to find a specific image right quick for you. So, in one part of this movie, this old guy here is in the bar, and they have a big container full of wheat, looks like. And so he pulls out one piece of wheat, and it hits this guy on the head. And he said, does this hurt? No, it doesn't hurt. But then he pulls the cork out of it, and all the wheat goes flying out and just desecrates him. So, you know, when we're talking about these screws, generally there's a lot of screws in there. And when you think about it, you know, you got one screw, but then you got multiple screws throughout the entire wall, and you can kind of get a picture of what's happened. All of those screws are trying to suck the heat out of that thing. So it is very important. And one of the things that I'm finding out with doing this bus is I don't do these. I don't screw in it at all. What I am doing is I'm using glue, and I'm gluing all my panels, all of my studs, everything to the walls, and then I'm attaching to the wood. That way I don't have that bridge so that I can lose that heat out through that wall. Does that make sense? Anybody else got some questions for Megan right offhand?
I've followed container homes for quite a while. I remember when I first discovered it, probably over a decade ago, it was quite fascinating. But then, God, the industry taking off, and they're building hotels and everything else. But one thing that I've noticed common is, you know, when they first came out with that spray stuff, I don't know if it was foam or for bed liners, probably 20 years ago, a lot of guys that had trucks would have this sprayed in sort of plastic bed liner. I think they're using a similar material the spray on the outside to insure against rust. I think that's rather common now. I don't know what it's called, but they first started doing it in short bed liners. I think it's the same stuff they're using for container homes.
I find the rust issue kind of interesting. I've seen people who do actually appreciate the rust aesthetic, and because shipping containers are made out of core 10 steel, which is designed to rust to a certain amount and then never rust anymore, you can actually even bury a container in direct contact with earth, let it rust, and know that it's never going to be compromised completely. It'll still remain watertight.
So it kind of patinas.
Yeah. Core 10 was, that's one of the aspects of the design. They know it's going to be out in salt water. It's going to experience a lot of issues. And one of the things they did was just go ahead and design it to rust to a certain degree. It's not always what you want in a home, certainly. And not everybody appreciates that look, but if you like that rusty patina, you can go with it and know that it's still not going to rust all the way through your wall.
When you're saying core 10, is that the number 10 or TIN?
10, the number 10. Core 10 is the rating for the steel for the shipping containers.
Gotcha. Anybody else? Very good.
I
did think one thing that she might not have mentioned as a con is obviously, like with some of the other construction, you got to consider the expense of a crane because, well, flatbed to haul it and a crane to lift it. So that's an expensive cost just to get it situated.
And, mentioned briefly, but really extremely important is that there's only some certain ways that you're going to be allowed to use these with building codes. You got to really maintain that awareness. You can't just plop one of these down on a slab and then build a house on top of it. They won't rate it as a foundation.
I've found out that if in most cases, when you're doing some kind of odd building, if you help educate the inspector, he appreciates that. And a lot of times he'll work with you. Once in a great moon, you're going to get that one inspector that's just hardcore, balls to the walls, by the book, but really, now, like for instance, in Morganton, Mike Crotts is the building inspector here. And he is, oh my God, he is so impossible sometimes. But basically, if I wanted to build this here, and I go to him and I show him the plans and everything, and he's going to say, well, this is not in the code, but I'm going to tell you what. And matter of fact, he sent me something because I had a question the other day. A student had asked me, and I want to just share exactly what he said, verbatim. Somebody had asked me, can red heads be used in place of J-bolts for the foundation? And, he said, no, according to the code, it can't. But if you get me a signed, sealed drawing from an engineer, you can do it. So, that's what, he would say about something like this. It's not in the code book, but if you get an engineer who's a lot smarter than he is that says it will withstand, then he'll accept it. And I think that's the case in most places. I know Asheville, they're pretty hard on contractors. It seems like, that you got to have 3 sets of plans submitted. You got to have, it takes 2 to 3 months to get the plans approved. And maybe that's just the number of builds that's going on in there. But here in Morganton, I submit one, I don't even have to submit an entire plan. All I got to submit is a floor plan and a wall section. And he's got a pre-printed wall section, where I can go through and just write stuff in and of what the material is going to be. And I actually drew that for him. And so, that's all it's needed here. So it really depends on the building inspector, for sure. Any more questions?
Yeah, what was the term you said at the beginning of this that they wouldn't allow, but I didn't hear the word?
The as-is containers, is that what
No,
you're talking about?
no, what Eric just said when he started that last dialogue, I didn't hear the word he used for attachment or whatever. That the code wouldn't allow. I didn't hear you.
Eric was talking about redheads on foundations.
Oh, yeah.
What are redheads? I don't know that term.
It is a very big TAPCon. Do you know what a TAPCon is?
Yeah, I've used those. I know what a TAPCon is.
Okay, well, it's just a big, it's a, you know, it's just an oversized, oversized TAPCon, really.
So you have to use that explosive gun like a firecracker?
No. So redhead, we call it redhead. It's really, it's either a wedge anchor or it's a screw anchor. And you can use these in conjunction with epoxy. So you can basically, you got to drill a hole and you got to pop these down in there. And like this one here, for instance, when you tighten onto the stud that you're, or whatever you're fastening to, then this pulls up and spreads this out, and it connects to the concrete. These can slip if the hole is made too large. This will pull completely out. So, you know, with a J bolt, you pour concrete, you put your bolt down into it, and it's a done deal. There's not a whole lot of science behind using the J bolt, but with these, there is more error. There's more room for error, and they are not allowed in the code book. But if you have an engineer's signature, then you can use this. These type of screw ins, again, they're made by the Redhead company, and if I'm not mistaken, I think Redhead and Tapcon are one and the same. And so these type of bolts here, if you ever go into a tunnel, not necessarily the tunnel at Tunnel Road, but some of the larger tunnels up in Pennsylvania and other parts of the country, your sealing material is held in place with these type of bolts. Basically, they drill a hole that's much bigger than this. They squirt it full of epoxy and then screw this into it. And once that epoxy sets up, you couldn't pull that, you'd pull the concrete down before you ever pulled that epoxy out. It's just, it's just the way it is. So that's a Redhead.
Okay. They use Tapcons, a larger diameter, in manufacturing for anchoring conveyors and equipment, because I remember having to get them out and put them in.
Yeah.
So what are the ones called where you fired in with that gun that you, like a firecracker thing,
Powder actuated.
Say that again?
Powder actuated.
Yeah, that's a loud gun too when it goes off.
Powder actuated tools like that.
Yeah, I had to use that before.
Yeah. So these are again, they're kind of iffy. The building code doesn't like using these because of the way that they're put in. So again, it's kind of a crapshoot whether these are going to hold really good or not. And you're technically supposed to be certified to use this. Now, you can go down to Lowe's, Home Depot right now, and you can buy one of these things, and you can buy loads 1 through 4. There are 8 loads in this. If I put a number 8 in it and I tried to shoot through a 12-inch concrete wall, I'm probably going to end up killing my neighbor because it's going to go through the wall and about 2 or 3, 5 miles away. It's it's got a lot of power in it. It's like going from a 22. If you're familiar with guns, it's like going from a 22 to a 12 gauge high power slug. I mean, it will kick the piss out of you. And so to be certified in this, you see how many different manufacturers they are. So you can't just get certified in a powder actuated tool. You got to be certified for a Ramset master shot by Ramset, or a DeWalt, or a Hilti. So, there you have to be certified by the manufacturer for their specific guns. And so, it's kind of a, like I say, it's kind of a crapshoot. Okay, any more questions for Megan? All right, so let's see who's up next. Da, 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 da.
Mr. Anderson.
Mark Anderson. Let me see here. Stop sharing. Take it away from Megan and give it to Mark. Where are you? Well, Mark, are you even here? Mark Anderson is not here.
I don't think so.
He's not showing up in the list.
I don't know.
President's Day off.
What's that?
Must have took President's Day off.
Oh, yeah. Well, let's see. Who's next? Danny is next.
That'd be me.
All right. You are 3D Harvey.
Yeah,
Okay.
on the different computer today.
Okay. All right. Okay, sir, you now have co-host.
All right. Good morning, everyone. My name's Danny Harvey. This presentation is on passive solar design. And as we know, the sun releases a lot of energy. A lot of that energy reaches our planet, and a lot of the energy that we use on our planet comes from the sun. Sun releases a lot of energy all the time in various types of electromagnetic radiation at a number of different high frequencies. Visible light is almost half of that energy output. The amount of that solar radiation that's reaching the outside of our Earth's atmosphere is given as 429.2 BTUs per square foot per hour. That's referred to as the solar constant. And that amount of energy is approximately 35,000 times our annual human energy use. So every hour, the surface of our planet is receiving nearly 35,000 times the amount of energy that we use every year. Now, a lot of that energy is reflected by our atmosphere. So nearly a third of that energy gets reflected back out into space, but about 70% of that energy reaches the Earth's surface, where it is either reflected again, transmitted, or absorbed into the surface. Once it's absorbed into the surface, it later radiates back out into the atmosphere. So we have a lot of energy transfer happening all the time from solar radiation. Passive solar design is a means of building that uses that solar radiation and captures and stores for reuse and transfers that energy through non-mechanical means. Active solar systems would be like a solar panel that is actively transferring that solar radiation into electricity. But passive solar design simply uses the energy that's reaching the surface of our planet all of the time. We've talked about a number of ways that heat is transferred. We've talked about radiant energy. Everything radiates energy. The sun radiates a lot of energy, and that energy reaches us through a void. There's nothing in space for that energy to transfer through, so it's not conducting or convecting through any material. So there's no medium that energy is transferring through. It's directly transmitted to us. Conduction is that energy transfer through a solid material, and all materials that have mass transfer energy at their given rate. Convection is an energy transfer through a fluid that includes gases and liquids, and passive solar design utilizes all of these methods of energy transfer. The amount of energy that we are receiving at any one time is affected by the path of the sun. The solar trajectory is something that varies across the surface of the planet, and it's going to be dependent on what latitude you are and at what tilt the planet is at any given point in the year. So that amount of energy that we're able to receive varies according to how directly we're receiving it. In the summer, you can look here, we've got direct overhead sun and it's coming straight down at us. We're receiving more of that direct heat energy. And in the winter, when the sun is lower on the horizon, the angle of incidence changes the amount of energy that gets reflected. So we receive a little less energy during that time. And that angle actually spreads the amount of energy over a greater surface area. So we don't receive as much energy in any one small area. So the amount of energy received per square foot changes. We can utilize that information in siting our buildings by knowing what latitude we are and what the angle of the sun will be at any time of the year, and orienting our buildings to collect as much of that radiant energy as possible in the winter and not collect that radiant energy in the summer when we want to be cool. The orientation of the house along the east-west axis, the longest dimension being on the southern side, increases the amount of exposure on that side of our building, allowing us to capture as much energy as possible in the winter when the sun is lower in the southern sky. Having a downward slope on the site may increase the amount of time that the sun is in direct exposure to the house. And then in times when we want to reduce the amount of solar heat gain, natural shading, things like trees, overhangs, or terrain changes can provide natural shading to areas of the house that we don't want to receive as much direct solar energy. And weather exposure. We have a lot of northern winds and other things that affect the energy use of the house, and we can site our house accordingly to reduce any unwanted impacts. Elements of the passive solar design can be used in any part of the world. Of course, if you're on the equator, your sun's going to stay directly above you at any time of the year. But anywhere else in the northern and southern hemisphere, if we orient the building toward the equator, then we're going to be receiving the most amount of sun in the colder months. You site the longest dimension of the house along the east-west axis to provide as much southern exposure as possible. Maximize the amount of glazing on the southern exposure, and I'll talk a little bit more about glazing as we go. Typically, you'd only want to use about 1/3 to 2/3 of the square footage on your southern exposure for glazing. It's possible to have too much glazing. So when I say maximize, I don't mean make the entire south side of your house a giant window. Minimize the eastern and western glazing to avoid your increased summer heat gain. In the summer, if you've got a large western window and that sun's beating in, it's going to be providing a lot of heating in that space in a time when you want to keep it cool. Shading your glazing in the summer, again, will reduce the amount of unwanted heat gain. And the core elements of passive solar design are storing that energy that the sun is providing in a thermal mass that allows it to be conducted in the space and to radiate into the space. And that helps regulate the temperature throughout the day by having it stored in a thermal mass. And then, of course, as with most green buildings and energy efficient buildings, we want to insulate and air seal sufficiently so that we're not losing our desired heat and we're not gaining undesired heat in the summer. Looking at the image above, it's a somewhat typical passive solar home plan in that we have a large amount of glazing here along the southern side. They actually have a sunroom here that's collecting some heat. There's a lot of glazing along this south area. And here on the west, this is all a sunroom with a porch. And they have interior windows as well that allow that solar radiation into the main space during the day. And these windows can be shaded when necessary. I'm going to talk a little bit more about those ideas as we go. There are two main types of passive solar design. The first is a direct gain passive solar, where the interior space is heated directly by the solar radiation. The sunlight coming into the home is captured and stored. We see that there's south-facing glazing. The windows allow that sunlight into the home. The solar radiation is transferred inside the space and then stored in a thermal mass that then slowly releases that energy throughout the day. And then having a good insulated building envelope allows that energy to be in the areas that we want it and not to escape where we don't. The other type of passive solar system is an indirect gain system, where the solar radiation is actually captured outside of the building. It heats a thermal mass outside the building, and then that heat energy is transferred into the interior, either through conduction or convection. You can see in this example here, we have a greenhouse that has acts as a solar collector here, where the solar energy is able to enter that external space, heat up a thermal mass, which then conducts to the inside, but then is also open to the air inside, and the hot air moves towards the cool air inside, and the cool air is then drawn out and through the space, creating a convective heat loop or a thermosiphoning action. I'll talk more about that as well. Two primary types of indirect gain storage systems are thermal storage walls. There are a number of different types of thermal storage walls, and roof ponds, which are a little less common and a little bit more complicated, but also very effective. Thermal storage walls absorb and store the radiant energy and then release that energy into the interior space. They tend to be constructed out of masonry, and they tend to be dark colored to absorb the most radiant energy possible. In this situation, you can see it's somewhat like the greenhouse idea, just in a smaller system, where you have a glazing that is a short distance away from the thermal mass. The thermal mass collects solar radiation from the glazing. And in this situation, there's ventilation that allows that air in the space, once it's warmed, to transfer into the interior, heating that space. And as it moves in, it's also drawing cool air at the bottom. So it's providing some ventilation in that space as well through a convective heat transfer and somewhat of a loop being created. One of the most well-known examples of this is called the Trombe wall. Here is the best picture I could find of that, and I apologize for the resolution, but it's a building that was built in France in the 60s. And these spaces here that look like windows are all actually thermal collectors, where there's a thermal mass behind a piece of glazing, and you can see that it's painted a very dark color. And that captures heat and then moves it into the interior through conduction. I talked about the vented assemblies. This is a vented assembly where there are pathways for air to move at the top and bottom of the wall. The radiant energy is stored in this thermal mass and is also convecting I'm sorry, it's conducting through the thermal mass and then radiating into the space, while the air in this area, excuse me, go back one. The air here is heating and transferring in towards the cooler air. The cooler air is getting drawn into this area and creating this convective loop. In the unvented assembly, there's no air movement through that wall. The radiant energy is simply stored in the thermal mass, and as the thermal mass heats up, it then conducts into the interior and then radiates from that thermal mass into the interior over the course of time. And this is a generally far more measured amount of heat transfer. With the convective heat loop, you have a lot more heat in the middle of the day and the air moves more quickly. In a unvented assembly, that's your air movement inside is not being affected. You're simply conducting energy through the wall and then radiating it into the space. There's some examples of roof ponds. Some advantages of roof ponds are that they maximize the amount of surface area. It's often able to have more square footage on a roof surface than you are able to have on a wall surface. So you get a lot more surface area to collect radiant energy. And roof ponds are able to both heat and cool. In the summer, that's actually preventing some of that heat that would normally be hitting the roof and transferring through the roof into the building. It's slowing that heat process, that heat transfer process a lot more than a typical roof assembly would. And that heat is stored and releases gradually. There are some direct transfer methods. You see here, we've got a pond directly on top of a building. And there are some indirect methods where you have storage tanks that use water as the thermal mass and then uses piping to move that energy to another area inside a building. So here are a number of examples of passive solar design in both a residential and a commercial space. This is a project I worked on in Atlanta that has a residential learning area and a commercial learning area. This is the South Face Energy Institute, and they started out as the Georgia Solar Energy Coalition. They've used both of these spaces to highlight a number of different types of passive solar design. You can see that there is a lot of glazing on the south side of the building. These are the south sides of the building. There's not a lot of glazing on the east and west sides of the building. And where there are windows on the western side, it uses a mechanical interior shading to prevent unwanted heat gain in the summer. There are a couple of interesting things happening here. You can see that there's a lot of shading for the south side of the building. And one of the ways that we're using shading here also is to allow indirect sunlight to transfer into the space by bouncing off the top of this shading. Another interesting design feature to me on this one is that these overhangs here were actually sized so that on the summer solstice, when the sun is highest in the sky, the shadow reaches to the bottom of these windows on the lower floor. So you're actually able to shade most of the windows during the points of the highest amount of heat gain. You can see a couple other solar ideas happening here. These are active systems. This is an active solar shingle. And then we've got some passive solar hot water I'll talk about also. All passive solar systems utilize thermal mass, and thermal mass is what we store the radiant solar energy in, how we transfer that energy into the space. Typically, walls are made out of high thermal mass materials like concrete, stone, and brick. Floors can be made of concrete, stone, or ceramic tile. Interior elements include cement plaster or masonry fireplaces that are oriented and sited in a way that they become thermal mass and are used to radiate that energy back into the space. And we talked about water with isolated storage, and roof ponds. There are a number of other very high thermal mass and high R value insulations available. And the amount of energy that is transferred through that material, you can see here, is rated at heat capacity and thermal conduction. So something like the metal of the shipping containers that we just saw has a very high rate of conduction, and something like a brick wall or very dense concrete or a insulated concrete form that has concrete and a insulated material over that can have a very slow rate of thermal conduction. That allows that heat to be radiated out into the space at a much more regular rate. Talking about the glazing on your building, it's important to know what your solar heat gain coefficient is for your windows. The solar heat gain coefficient is the fraction of that radiation that is actually transmitted into the space. A lot of your radiation is going to be reflected off of the window. A lot of the radiation is going to be absorbed by the window, and only a fraction of that radiation is transferred into the interior. When you're designing for passive solar, you may want more energy transmitted into the interior than you would have in a typical window. You might want a very high solar heat gain coefficient so that you get a lot of energy that's transferring through that window. And on your east and west sides, you may want a window that's much different, that does not allow as much energy to transfer through the window. Something that's important to know with solar heat gain coefficient is that rates the entire assembly. So it's actually testing how much energy is being transferred through the entire window assembly, the casing, the frame, and taking that into account for how much energy is absorbed. Something you may see more in a commercial setting is shading coefficient. And the shading coefficient is rating the glass only. It's not looking at the transfer of energy through the window assembly. This might be important in areas where you might be fabricating the window yourself. It might be a type of window that's not available pre-manufactured. You might just be building a new window out of a piece of glass, but you want to be able to know exactly how much is transferring through that piece of glass. And like I mentioned, you may want to use different levels of heat gain coefficient in different areas of the house. Some parts of the home you may want to be getting a lot more energy through the window. And the way that the windows are rated for their insulation value is the U value. That's the inverse of the R value. We want to have a higher U value for your east and west facing glass that's going to have a lot more direct sunlight in the early morning and in the late evening. But then it's also something that's important to consider for your south facing windows, because as I said, if we have a third to 2/3 of our entire wall square footage made up by glazing, that's a large amount of area that has a very low insulation level. So if you did end up designing a house that was all windows on your south side, that entire side of the house may have an R rating of less than 4. And if you have one whole wall of your house that has only a R4, you're going to have a lot of heat transfer through that wall at times when you don't have the solar collection happening. So at night, when there's no sun coming through, you'd be losing a lot of heat through that. And in areas where you're going to have a lot of cooling loads, you could be transferring a lot more heat into the house during the summer than you would like. This is also one of the areas that you can run into a lot of high costs for passive solar design. The better the windows you want to use, the higher the cost is going to be for your project. And there are a lot of different types of glazing options out there. I've looked at a couple down here that are typical clear double glazing, or a double glazing with a coating, or a double glazing with a gas. And we've seen low E windows and argon filled windows that transfer heat at different rates. You know, if you start getting into triple panes and insulation, you can really add a lot of cost to the project, but it does come out in the long run if you design properly. Based on the amount of energy that you're using, you can have some energy savings that pay off those windows in the long run. These insulation materials, you know, there's many options for insulation material, and there are various areas that you may want to use different types of insulation. The framing techniques that you use in your walls will maximize the amount of insulation in the walls, and that can be very important in the passive design setting. Remember, if we're not heating the house actively, if we're trying to use just the energy from the sun, we don't want to lose the energy that we've gained from the sun quickly. So capturing it, storing it in the house, and not letting it escape quickly becomes very important. Air sealing improves your insulation performance. The less air that's moving through your building assembly, the less air that's moving through the insulation material, the better it's able to capture and store heat. And high thermal mass material will release that heat much more regularly. You can see in this graph here, the dotted line represents a typically insulated wall with a low thermal mass. And you can see how that curve matches the temperature of the outside as it goes throughout the course of the day. But a high thermal mass wall will stay much higher than the lower troughs and not raise to the high temperatures that we see in the outside. So it's regulating that curve and making that heat transfer much more even. This picture here is an insulated concrete form. So when the concrete is poured into these forms, it is insulated on both sides. This is an expanded polystyrene insulation material. And that creates the density of concrete to hold that thermal energy, and also creates that insulation layer that keeps that energy from conducting to the outside quicker than we would like. From that previous picture of the South Face Energy Institute, that commercial side of the building was all insulated concrete forms. That was 4 stories of insulated concrete forms, which was an interesting thing to work with. I'll say that. The isolated solar systems are a type of indirect storage that we talked about, where the heat is actually captured outside the building and then moved into the interior. This diagram shows a panel. Again, it's a painted panel that's a dark color to absorb as much heat as possible. This panel is located outside the interior wall. It has glazing over it and is a solar collector, allowing the radiant energy to heat this panel. As the air in that panel is heated, it is moved up and into the house. And as that hot air enters the space, it's drawing cool air from the space back into the panel to again be heated and create that convective loop. And so passively moves air and heat into the space. In this situation, the example given for the thermal mass is this food to be dried, but this is a very common design that was used early on in passive solar for an external collector, where they would actually use masonry or stone in a box like this, and sunlight would heat that thermal mass, and as air is pulled in, it transfers through that thermal mass, and that heat is transferred to the air, and the warm air is then allowed to enter the space. That's something that you want to be able to control during the seasons. That sometimes you'll want to have that hot air coming into the house, and that sometimes you will not want to have hot air coming into the house. And I appreciated some examples like this. In this, the thermal mass is actually able to be a part of the external wall, and as that air is moving through the thermal mass and heating the thermal mass, it's also transferring directly, it's conducting into the space and radiating into the space in this type of a system. These isolated solar systems also include some hot water systems and some radiant floor systems. where the heat is stored and transferred into the inside of the house in different ways. There are a number of different types of heat storage. We talked about using a water, a masonry, or a concrete for direct heat gain. You can see in these situations where sunlight is able to hit the water and heat it up, or it's able to hit the stones and heat the stones, able to hit the concrete, and that heat is absorbed in that material and then slowly radiated into the space. That indirect gain is transferred from an external mass and then moved into the house. And in a solar radiant water, we have what is an evacuated tube system that has a liquid in these tubes. That liquid is heated, and then the hot liquid, the heat in the liquid, is transferred into the home. That can be used in some radiant floor systems, but is most common in the passive solar hot water systems. The passive solar hot water systems use a thermal collector to store and reuse that radiant heat. That is often a typical storage tank, a hot water tank, where as the water is heating up, it's being drawn into the hot water tank on a convective loop. The natural thermosiphoning occurs, and the hot water is moving in to the storage tank. And as the hot water moves in, it's replaced by cooler water from the storage tank. And that is a natural thermosiphoning loop that is happening without a mechanical means. It doesn't need a pump. It's naturally thermosiphoning. The different types of storage tanks can be used in different ways. These are external storage tanks, so that's all happening outside of the house. And then when we want hot water, we call on it, open up a tap, and the hot water from the tank is moved inside. Some indirect systems actually use the storage as a thermal mass inside the home, and that thermal mass then also radiates heat into the space. So that can be another type of indirect heat transfer and an indirect storage system. We're looking at our orientation, our design. It's important to think about what type of room is being, what type of use a room has, and where we're siting them. If you put all your bedrooms along the southern wall, but you're never in your bedroom during the day, it might be getting all of that heat and light, and you're not actually utilizing it. You want to utilize that natural illumination in the spaces that you're going to be using during that time of day. If you site the kitchen along the eastern and southeastern sides, you're going to get that morning sunlight when you're in the kitchen in the morning. You got your daylighting in your main openings in your larger common spaces during the day. That can reduce the amount of reliance on electric power for lighting. And with a lot of passive solar design, when we've got our house oriented to the south, then the areas on the northern sides don't receive as much sunlight, and we can use other means to get natural illumination there. These solar tubes allow radiant heat, radiant light to transfer into interior spaces that don't have external windows. And then a design that we've seen used a lot over the course of time, and not just recently, but for hundreds of years, is this idea of a clerestory, window on the second story that allows light to enter all the way to the back of the home. So a couple of different ways that you can utilize a passive solar daylighting to get light to spaces that wouldn't otherwise have a direct solar path, and that can eliminate some of the energy use that you would normally have by having electric lights. The skylights and roof angle affect the amount of heat gain to the space. A lot of people really enjoy using skylights, and as I just talked about with natural daylighting, you might need to use some skylights to get light to some areas that wouldn't otherwise have them. If you've got a skylight on the northern roof, then it's not going to receive as much direct sunlight, except in the summer. And on the, if you've got skylights on your southern roof, it's going to receive some really direct sunlight in the summer. So you may want to have some types of mechanical shading options. You may want to have a way to eliminate direct heat transfer when you don't want to have that direct heat transfer. You can see a roof like this that has a very shallow pitch and a lot of glazing, that's going to absorb a lot of direct solar radiation throughout the summer. So the cooling loads in this space would be pretty extreme. And the orientation, the angle of the roof could also greatly increase the amount of solar radiation that you're gaining in situations where you want to. So if you're in an area that you want to gain a lot of heat in the winter and you're up in a northern latitude, you may want a very steep pitch to match the angle of the sun in the winter to gain as much light and heat as possible. So designing your roof angle correctly will, for your ideal situation can have a big effect. And it's important not to have too much glazing in a space and create a greater cooling load in the summer than you're gaining from the heat that you were gaining in the winter. You could be actually using more energy to try to cool the space if you design it improperly. I'm having a feeling I missed a slide. I may have skipped a slide, and I'll go back and look and see if I missed one here. But ventilation is designed. You can design a house to use passive ventilation, where the heat transfer, the radiant energy in the house actually encourages ventilation. Open floor plans that encourage ventilation, but then using natural stack effect and convection properties can encourage the natural ventilation so that you don't need a mechanical fan or anything to actually move the air through the house. In these situations, you can see here we have what is like a chimney, and in this drawing, that's what this channel is right here. As the sun strikes that and heats that air up in that column, it is exhausted through the top and then pulls air in through the bottom to make up the air that is pulled through the space. And here we've got some vents that are pulling hot air out of the space and vents that are allowing cool air into the space. And so you can actually utilize that natural heat transfer to bring ventilation air into the space and avoid some of the cost of using a mechanical fan to move air through. I did miss one slide that I want to go back and find here. Yes, here's my shading slide for the glazing. It's extremely important to shade your glazing on your south face to avoid unwanted solar heat gain during the summer, so you don't have an increased cooling load. And there are a number of different ways to do that. You can see here on this commercial building, there's a small overhang that shades those windows when the sun is at its highest spot, but then allows the sun to hit the windows at times that we want to have that direct solar radiation. There are a number of different types of shades, awnings, screens, porches, natural shading like trees or trellises or vines that we can use on east and west faces to eliminate unwanted heat gain. And then something else that's interesting also is the angle of the windows and how that can be used to change the amount of direct heat gain that we have. In this situation, there's an overhang. If we had a vertical window, when the sun is at its highest point in the sky, it's going to be, the overhang will be completely shading the window. In this situation, they've actually angled the window out at the top so that the window itself would never be in direct exposure to the sunlight. And when the sun is lower in the sky, that angle is also diminished. So it's not actually going to be receiving as much direct energy as it could be, but it's reducing the cooling load. So if you're in a situation where you have far more cooling needs than heating needs, angle of the window can change the amount of heat that's entering through the window. And then conversely, if you want to heat more than cool and you want to accentuate as much heat as possible, you might angle the window the other way so that it's collecting as much heat as possible in a heating climate if you're trying to capture as much heat as possible. There's an example of that in my last slide here. You can see that those windows are angled to capture as much of that winter sun as possible. So in conclusion, a passive solar design is a very old way of using the natural heat that's available in our environment to heat our living spaces. We've talked before about Mesa Verde here, where there's a natural overhang that shades the buildings during the summer to keep them cool. And then as the sun is lower in the sky, direct sun is able to heat these walls, which are a adobe that are able to capture a lot of that thermal energy and then slowly radiate them back out. And in much of passive solar design, we are using a lot of these natural ideas to and mimicking that type of environment. So we create these overhangs that are a lot like these natural overhangs and use a thermal mass that is a lot like these natural thermal masses. And by doing that, there can be a lot of upfront cost in design, in material, in planning, and other considerations to make sure that you're getting the most efficient use of the space, the material, and the site, the other design elements, including your glazing and your ventilation. You can spend a lot up front. The cost can be very high, but then ideally, your monthly cost to heat that space or cool that space is far lower than it would be if you were using a combustion heat source or any other type of heat source. So over the long run, you can have an energy payoff where you've actually recouped the cost that you spend on this building. And it's a design that I think is going to be far more important in the future as we continue moving away from fossil fuels. And it's worthwhile to point out also that the reason that we got to where we are now was, as far as our building design and not using these type of ideas, is because of our reliance on fossil fuels and our ability to heat spaces with combustion, whether we're burning oil or coal or natural gas, and relying on the heat that we're generating from hydrocarbons instead of using the heat that's around us and naturally occurring and free. That is my conclusion. Here are my references. I highly recommend anybody take a look at especially Krieger and Dorsey's Residential Energy. And then as we're going on, I'm sure we'll end up talking about Joe Stiebrick's Builder's Guide for Mixed Climates. But a lot of my material here is from the 1979 Passive Solar Energy book from Ed Masria. And that just shows you how little some of this has changed even in the course of several decades. They're all very simple principles that are still in use today and remain unchanged because of how basically sound and correct they are. Thank you.
Wow, I'll vote you get 100 plus. Eric, you could teach a whole course on this by itself. You're muted.
There is a whole class on this.
Oh, it really is?
Yeah.
I didn't know that.
Questions?
Phew.
That's pretty thorough.
Well, this last slide here with the Adobes, are those window looking things? Or those would those be the solar? What you call it?
Actually, no, in this situation, in this picture, this is just glazing. You can kind of see in through here. And actually, it's the same picture, same building as this. So that's the inside of the last picture you were seeing there, where those are the adobe walls. These windows are angled to capture as much of the direct sun exposure as possible in the winter. And then there's a thermal mass in the floor, thermal mass in the walls that collects and radiates that heat back to the space.
Well, that looks like a really nice room. I'd love to be there.
Yeah.
That's
Also
an
notice
Earthship,
the
is it not?
Say again, Sam.
Is it an Earthship?
This one is, it's bermed into the hill, yeah. I mean, it depends on your definition of earthship, but this one uses some, some grading to also encourage less conductive heat transfer through walls by having them in the, bermed into the earth.
Cool.
Also notice the vegetation in there, in that room.
Sure, yeah. And a lot of, my first experience with this sort of thing was an indirect system that was a greenhouse outside. And of course, in that situation, you also have to be very careful about your moisture transfer, because you end up with a lot of moisture in a greenhouse that you might not want to bring into the space. So if you're using an indirect system like a greenhouse, you might not want to use a vented system necessarily, or you might want to have other means of controlling moisture entering the space.
I'm gonna take over for just a second. So you talked about trajectory. Let me find it. Okay, so you talked about trajectory in the glazing. Maybe I can find it.
It's up towards the top there.
Okay,
Roll it
there we
down.
go. There we go. So, all right. So, question, and I know you'll know the answer, so I'm just picking on you a little bit. Okay. So as we know, here's our Earth, and actually let's start again. Here's our Earth. No, let's try again. Here's our sun. I'll get it right in a minute. And we have our Earth here. We'll make Earth blue. And so our trajectory around the sun does kind of that. Now I'm exaggerating a little bit. So this is our winter. We're over here in winter. So why doesn't how come our winters are cold?
Because we're in the northern hemisphere and the axis of the planet is tilted away from the sun during our winter months, we have that indirect reflection. We've got a different angle of incidence on the surface of the Earth. So in situations where we're on the other side of our orbit and the northern hemisphere is tilted towards the sun, that energy is more directly focused towards any one spot. And so more energy is transferred directly at that spot. And when we're kind of tilted away from the sun, the angle of incidence is greater. And so we have less energy that is able to be transferred to any one small area. And I wish I had your bundle of straws, Eric, because if you take that bundle of straws and you put them all together, you can see that all of the points of those straws are going to hit in a small circle, and all of the points of those straws are going to hit that small circle. But if I angled all of those straws, then that circle becomes oblong and gets stretched out, and less of that energy is focused in the smaller area, and more of that energy gets dispersed over a broader area.
Very good. Very good. so our atmosphere plays, he was talking about, so the atmosphere being a problem here and where our latitude is, our orientation, the slope, and all of this. So that plays a huge, huge part of how much sunlight gets in. Obviously, when we're talking about those tropics, then the sun is overhead all the time, and we're getting, again, 100% of the sun. And so when we're up into, the northern and the southern hemispheres, then because of the way this tilt is, we're getting some of this deflection. Now, in Australia, when they're down here, they're getting more direct sunlight in the summertime, or their summer, our winter, their summer. So let's say summer here, and then so this is northern hemisphere, this is southern hemisphere, and then we have our summers, and then they have their winters. But because of the way the tilt is, even their winters are going to be warmer than our winters, and their summers are way warmer than our summers. While we're still on that notion of tilt, I want to applaud you, because you are probably the first person that has ever talked about the window tilt. And so this is huge. So let's think about something here for a second. So when we're talking about this window tilt, so we've got the wall coming in, and we've tilted our windows back a little bit. The sun's coming in. Notice that they're talking about the incident of angle here being tilted 78 degrees. And so why is that? We've got this coming down through here, and the 90 degrees coming off of there, and that's what they're talking about there, 70. I don't know why they point out 70, is it 73, 78 degrees? I don't know why they point out 78, where this is what is super important. Anytime that you are less than 15 degrees, light cannot enter glass. Okay, so let's think about fiber optics. All right, so we have a clear fiber here, and we're going to shine light into the end of it because the end is 90 degrees. And what happens is that light is captured and cannot come out of there because it's less than 15 degrees until it gets to the very end, and then it can come out. And by tilting these windows, and I've only seen this in very, very few examples, by tilting this glass when the sun is high up in the sky there, then light cannot penetrate that window, or at least, we have some visible light that we can see, but the UV rays and so forth are not going to be able to penetrate that, and they bounce off, and we don't have the heat gain there. So bravo on that. Another problem that seems to be an ongoing argument. I want to get your view on this. Low E windows. Low E stands for emissivity, which is the transfer of UV rays through glass. So the code actually says that south facing windows must be low E windows, and that's in the code. You have to do that. So arguments there have been, well, that takes away from our UV gain in the wintertime. What is your anything that you've come across there in the past or in your research?
I feel that it's probably okay to still continue to ask for those to be low emissivity, and that you can account for the difference in heat gain through adding glazing where you want to and where you can. Unless you're in a situation where you really just are trying to capture every single little bit of heat that you can, and not use any extra heat source. You know, if you're relying only on solar heat gain, I could see where you might have a bone to pick about having to use low emissivity. But otherwise, because of the way that the house is going to use energy throughout the times of the day when it's not indirect sunlight, and when you don't want to have heating, especially in mixed humid climates, I think it's perfectly fine to continue to use low E windows in those situations. And if you want to have more heat gain in any one area, that can be done through sizing of the glazing and not necessarily the type of glazing that you're using.
That's one of the things, you know, because you get these, and I'm for lack of a better word, I'm going to call them fanatics, where they're trying to, you know, they probably squeak when they walk because they're so tight. They're trying to get absolutely every little piece of blood out of that turnip. And so that, yeah, I agree 100% with you. And, you know, again, you can upsize your windows to get more glazing area there to overpower that emissivity there.
If you want to use a low E window, then it can be used on in an indirect system. You know, you can use a non-low E window. If you want to use a window that allows all of the UV gain possible, then use that on an exterior greenhouse system, or use that on an exterior indirect solar capture system where you're heating up another thermal mass and then transferring that energy inside. And then you're not losing any of that extra heat gain that you could be getting, but then you're not also bringing unwanted heat gain into the house or losing a lot of your heat because of a higher conductivity through the window assembly.
Right, right. Okay, I want to give you a real quick story right quick. I had a student who built one of these things here, and basically these what's good about these little heaters here is, and let me just find a picture right quick. So there's different types, but he built one very much like this. And the good thing about these are they can be taken out in the summertime. Okay, so you put them in the wintertime, you take them out in the summertime, and they work very effectively. If you ever build these, what's going on in here? You see this mesh absorber. So this is a heat absorber in here that's generally black. And I've had two students build two of these. One of them decided to use tar paper, builder's felt, in this thing. And the other one decided to use petroleum caulk. And I'll tell you what, guys, if you've ever you ever talk about off-gassing, holy crap.
I was going to say, you don't want that in your house.
No, I mean, the builder's felt is nothing more than basically oil saturated or paper saturated oil, and I mean, and then that petroleum caulk, it stinks, it off gas like crazy.
Neither of those have the advantage of the mesh fabric, and the mesh is amplifying your surface area.
Yes.
Right? You want to have as much surface area as possible. The tar paper has a minimal amount of surface area.
Right.
I think the caulk.
Well, in the solar class, I gave them the option, and they didn't, this tar paper gets hot when, yes, it does. So, so the other one, the student that at AB Tech, he built one, and I've actually got this in the classroom. So he put that metal mesh in there, but when he put it in, he had it exactly straight. So he's got an opening where he pulls air in. He's got an opening where air comes out, and this was to go up on a wall or something. Don't put it straight. Make that thing curve. So that way the air flows in and around that and pulls off the heat and gives it to the air. So in my solar technology class, we talked a lot, almost 100% on passive solar and so forth. So I had a student who at Western Piedmont at another school, and they had a greenhouse, and she wanted to try to get this greenhouse effectively able to sustain life in the wintertime. So she went in here and she painted this wall black, completely and totally black. Now this thing faced south, this is solar south. Then she come in and she put in a whole row of 55-gallon drums and put water in them. And then on the floor, she had a black EPDM put down so that it would also absorb. Well, it did. It did really great. It, on our coldest days in the 30s and so forth, this easily reached 70 degrees. No problem at all. The problem was in the summertime, it was getting really close to, super high temperatures, and you couldn't grow anything in here at all. So one of the things, and in passive solar, it is equally important in passive solar to have passive cooling. All right, so you've got to have this, especially in our climate, we've got to go both ways. So one thing that we done here is we removed the water in these things and we put sand in it and then poured water back into it. So what happened was we ended up with an evaporative system in here. We added some vents that could be opened up here towards the top so that air would circulate through, and that brought this temperature back down to to about 80 degrees. And that was anytime that the ambient air was lower than 80 degrees. Now, if the ambient temperature was above 80 degrees, it was generally whatever the ambient temperature was, but we were able to get it below 110 on that. So don't, when you're doing any kind of passive anything, don't overkill at all. Any other questions?
On that idea you just demonstrated, was that a brick wall or a
No, it was wood wall.
wood wall?
Yeah, it was T111.
Okay, would it have been possible to install like pull down reflective shades in the summer to reflect?
Oh, yeah. That was something else. Sorry. Thank you. So there are big shade mats that you put over greenhouses, that's kind of like it's a net that just kind of helps shade. We use these, you can use these, and you can put them over the greenhouses, and you can also put them over chicken coops to keep animals, owls, hawks, and so forth from swooping in and grabbing your chickens and taking off. So the one thing that, and I don't know why it is, these are black. So even though, they're a great big net that's shading this, they would be more, they would do a better job if they were white or even, metal or something. I don't know, but white is going to reflect more of the light and not absorb anything in it. So,
Yeah, I was thinking along the lines of, like a silver shade. I remember growing up in the 60s, we had shades and curtains, but they didn't have a lot of colors. I think they had green, but I guess can you get any color you want or not?
I don't know. I have no clue. This is probably the coolest little thing that you'll ever see in passive solar. This is a solar wood kiln. So if you're going to be cutting any of your wood, that it has to be kiln dry. If we just leave it out here like that, the best that we can get in Western North Carolina is about 19%. But by putting into a solar kiln such as this, then we've got some fans in here. You can design this. Actually, Dennis Scanlon from ASU designed, made a really nice design, much similar to this, where you have, natural air outlets here that actually help circulate the air in here without the use of any kind of fan. You could put a DC fan in there with a PV such as this one. So if sun hits the PV, then it's going to be gaining energy here, and then it's going to turn a fan on, excuse me, to keep air going through there. So it's, these are really cool. And so you can do solar food dehydrators. Danny mentioned that a little bit. And so these can easily be homemade. And, this is the type that I'm usually accustomed to, which is much like the window unit that I was talking about. So you basically stack your food inside this little chimney here and on screens so that air flows through here naturally. Going back to that presentation, I want to actually bring up another thing. This chimney effect here. This is another, it's another rarity. You don't see it very often, but it is probably one of the smartest things that you could probably do. We've talked about, the ground being into the 50s, pulling hot air down in through this pipe, through here and into the house by a natural effect here. So chimneys don't always have to be for fireplaces. We can use chimneys, to help pull air into the house, fresh air into the house. And in this fashion here, then my concern is condensation in this tube here, because at some point, again, with that the psychometric chart, 95-degree air in Western North Carolina is generally about 80-90% humidity, and when we pull it into a cool environment, then we're going to end up having cool or have water condensate in here.
In any mixed humid climate, it's I feel it's really important to address that moisture before it enters your space. We've talked about ERVs and HRVs until that, there are a number of reasons to add ventilation in any situation, and so many of them don't take into account the moisture that you're bringing into the house. So
Absolutely.
particularly in what, we live in a rainforest.
Yeah, exactly. We do.
It's going to be really important to control that moisture. So yeah, just having a pipe that moves through the ground and then enters the house, you're not going to want that system. You're going to want to be able to filter it to keep out external pollutants, but then you're also going to want to be able to deal with the moisture that's coming in with that as well.
Mm-hmm.
And something to point out also about that is that stack effect happens without the sun, right? It's not relying on the sun for that stack effect. We're just creating a pressure difference by having a chimney that is higher than the bottom of the house. So our natural pressure differences are going to create that air movement. It's not necessarily relying on the sun, but this example down in the bottom right corner, that's using both of those systems where you've got the sun heating up that space to also encourage greater energy transfer, greater air transfer. But that will happen all night long, regardless of whether the sun is on it or not, just because of the pressure difference created by the height.
Right. Yeah. If you've got a chimney in your house right now and you don't have a fire in it, you can feel a draft going through that thing. And that happens summer, winter, spring, fall. And that's why we put a damper on it. So we close the damper, we kind of seal that off so that we don't have, and the chimney can work in an opposite effect too. When cold air sinks to the ground, it can come down this chimney, so you can have a backdraft through there. And that's why sometimes you can have problems in really, really cold weather if the chimney is not built correctly. In other words, if it's just a great, a plain old solid shaft up through there, cold air will actually backdraft down through there and blow the smoke into the house. And that's I've seen that happen several times, just because a smoke shelf or the throat of it is not been put in place. Just And that's what that throat is for, is to help prevent that backdraft through there.
And we have reverse induction in this climate also.
Yeah, yeah, right. Any other questions?
This might be a silly one. Those rooftop ponds. You said something about those.
Yeah.
Yeah. Are those
Obviously, there's a
things
lot
that-
of issues with that sort of system, right?
Hmm.
You gotta be very careful about that system. You know?
Wouldn't it grow algae?
Sure.
Well, I was
yeah,
going to
you have
ask, are those safe to
have to
swim
keep
in?
it clean, just like a pool. I'm sure. You don't want to have that leaking into your house,
Obviously.
and then you're going to have to deal with some moisture. But what was your question specifically, Kobe?
I was going to ask if you could swim in those.
Yeah, why not, man? Make yourself a rooftop swimming pool and go swimming.
I mean, I know I've seen a lot of those in like large commercial buildings, or maybe on like, I know
Vegas.
some New York City have those, or some bigger cities.
Yeah, typically these are
On
actually
water.
far more shallow than a swimming pool.
Right.
You know, if it's 6 feet deep, then that energy that's hitting the top of the pool is not transferring very quickly to the bottom of the pool. You know, and you know, you're not going to get as much of a thermal advantage out of a 6 foot pool on your roof, and you're going to end up, you know, using far more power to keep your pool circulating and clean than you'd ever be saving by transferring any thermal energy into the house. So
And don't even get started on the structure to hold all that 6 foot of water, you know.
yeah, exactly. There might be some embodied energy in that steel frame you're going to need.
Or in the winter, if it gets too cold, the water can freeze, obviously, right?
Yep.
Well, in that situation, it can act as an insulator too.
Okay.
Well, I see that Mark is on here, and guess what, Mark? You get to go first on Wednesday because we're out of time today. So.
Sounds good. I'm sorry for the mix up.
Yeah, that's fine. That's fine. It happens. Okay, guys. Thank you very much. Again, I mean, obviously we're having a great time in this class because it just seems to go real quickly, and I hope you guys are learning a lot on it. So I will meet you back here again on Wednesday. Have a great day.
Thank you.
You too.